Radiocarbon dating is a method of determining the age of an object by using the properties of radiocarbon, a radioactive isotope of carbon. The method was invented by Willard Libby in the late 1940s and soon became a standard tool for archaeologists. It depends on the fact that radiocarbon, often abbreviated as 14C, is constantly being created in the atmosphere by the interaction of cosmic rays with atmospheric nitrogen. The resulting radiocarbon combines with atmospheric oxygen to form radioactive carbon dioxide. This is then incorporated into plants by photosynthesis, and animals acquire 14C by eating the plants. When the animal or plant dies, it stops exchanging carbon with its environment, and from that point the amount of 14C it contains begins to reduce as the 14C undergoes radioactive decay. Measuring the amount of 14C in a sample from a dead plant or animal such as piece of old wood or a fragment of bone provides information that can be used to calculate when the animal or plant died. The oldest dates that can be reliably measured by radiocarbon dating are around 50,000 years ago, though special preparation methods occasionally permit dating of older samples. While the idea behind radiocarbon dating is straightforward, years of additional work were required to develop the technique to the point where accurate dates could be obtained. Research has been going on since the 1960s to determine what the proportion of 14C in the atmosphere has been over the past 50,000 years. The resulting data, in the form of a calibration curve, is now used to convert a given measurement of radiocarbon in a sample into an estimate of the sample's actual calendar age. In addition to this curve, other corrections must be made to account for different proportions of 14C in different types of organism and different 14C levels in different parts of the biosphere. Measurement of radiocarbon was originally done by beta counting devices, so called because they counted the amount of beta radiation emitted by decaying 14C atoms in a sample. More recently, Accelerator mass spectrometry has become the method of choice. It can be used with much smaller samples, and gives results much more quickly. The development of radiocarbon dating has had a profound impact on archaeology. In addition to permitting more accurate dating within archaeological sites than did methods previously in use, it also allows comparison of dates of events across great distances. Histories of archaeology often refer to the early impact of the new method as the radiocarbon revolution. Occasionally, the method is used for items of popular interest such as the Shroud of Turin, which is claimed to show an image of the body of Jesus Christ. A sample of linen from the shroud was tested in 1988 and found to date from the 1200s or 1300s, casting doubt on its authenticity. Background, history. In the early 1930s Willard Libby was a chemistry student at the University of Berkeley, receiving his Ph.D. in 1933. He remained there as an instructor until the end of the decade. In 1939 the radiation laboratory at Berkeley began experiments to determine if any of the elements common in organic matter had isotopes with half-lives long enough to be of value in biomedical research. It was soon discovered that 14C's half-life was far longer than had been previously thought, and in 1940 this was followed by proof that the interaction of slow neutrons with 14N was the main pathway by which 14C was created. It had previously been thought 14C would be more likely to be created by deuterons interacting with 13C. At about this time Libby read a paper by W.E. Danforth and S.A. Korf, published in 1939, which predicted the creation of 14C in the atmosphere by neutrons from cosmic rays which had been slowed down by collisions with molecules of atmospheric gas. It was this paper that first gave Libby the idea that radiocarbon dating might be possible. In 1945, Libby moved to the University of Chicago. He published a paper in 1946 in which he proposed that the carbon in living matter might include 14C as well as non-radioactive carbon. Libby and several collaborators proceeded to experiment with methane collected from sewage works in Baltimore, and after isotopically enriching their samples they were able to demonstrate that they contained radioactive 14C. By contrast, methane created from petroleum had no radiocarbon activity. The results were summarized in a paper in Science in 1947, and the authors commented that their results implied it would be possible to date materials containing carbon of organic origin. Libby and James Arnold proceeded to experiment with samples of wood of known age. For example, 2 wood samples taken from the tombs of 2 Egyptian kings, Zusa and Sneferu, independently dated to 2625 BC plus or minus 75 years, were dated by radiocarbon measurement to an average of 2800 BC plus or minus 250 years. These results were published in Science in 1949. In 1960, Libby was awarded the Nobel Prize in Chemistry for this work. Physical and chemical details. In nature, carbon exists as 2 stable, non-radioactive isotopes, carbon-12, and carbon-13, and a radioactive isotope, carbon-14, also known as radiocarbon. The half-life of 14C is about 5,730 years, so its concentration in the atmosphere might be expected to reduce over thousands of years. However, 14C is constantly being produced in the lower stratosphere and upper troposphere by cosmic rays, which generate neutrons that in turn create 14C when they strike nitrogen-14 atoms. The 14C creation process is described by the following nuclear reaction, where N represents a neutron and P represents a proton. Once produced, the 14C quickly combines with the oxygen in the atmosphere to form carbon dioxide, CO2. Carbon dioxide produced in this way diffuses in the atmosphere, is dissolved in the ocean, and is taken up by plants via photosynthesis. Animals eat the plants, and ultimately the radiocarbon is distributed throughout the biosphere. The ratio of 14C to 12C is approximately 1.5 parts of 14C to 1012 parts of 12C. In addition, about 1% of the carbon atoms are of the stable isotope 13C. The equation for the radioactive decay of 14C is: by emitting a beta particle and an electron onto a neutrino, one of the neutrons in the 14C nucleus changes to a proton and the 14C nucleus changes back into the stable isotope nitrogen 1414N. Principles: during its life, a plant or animal is exchanging carbon with its surroundings, so the carbon it contains will have the same proportion of 14C as the biosphere and the carbon exchange reservoir. Once it dies, it ceases to acquire 14C, but the 14C within its biological material at that time will continue to decay, and so the ratio of 14C to 12C in its remains will gradually reduce. Because 14C decays at a known rate, the proportion of radiocarbon can be used to determine how long it has been since a given sample stopped exchanging carbon. The older the sample, the less 14C will be left. The equation governing the decay of a radioactive isotope is where NO is the number of atoms of the isotope in the original sample, and N is the number of atoms left after time t. I is a constant that depends on the particular isotope. For a given isotope it is equal to the reciprocal of the mean life that is the average or expected time a given atom will survive before undergoing radioactive decay. The mean life, denoted by I, of 14C is 8,267 years. So the equation above can be rewritten as: the sample is assumed to have originally had the same 14C/12C ratio as the ratio in the biosphere, and since the size of the sample is known, the total number of atoms in the sample can be calculated, yielding NO, the number of 14C atoms in the original sample. Measurement of N, the number of 14C atoms currently in the sample, allows the calculation of T, the age of the sample, using the equation above. The half-life of a radioactive isotope is a more familiar concept than the mean life, so although the equations above are expressed in terms of the mean life, it is more usual to quote the value of 14C's half-life than its mean life. The currently accepted value for the half-life of 14C is 5,730 years. This means that after 5,730 years, only half of the initial 14C will have remained. A quarter will have remained after 11,460 years. An eighth after 17,190 years. And so on. The above calculations make several assumptions, such as that the level of 14C in the biosphere has remained constant over time. In fact, The level of 14C in the biosphere has varied significantly, and as a result the values provided by the equation above have to be corrected by using data from other sources in the form of a calibration curve, which is described in more detail below. For over a decade after Libby's initial work, the accepted value of the half-life for 14C was 5,568 years. This was improved in the early 1960s to 5,730 years, which meant that many calculated dates in published papers were now incorrect. However, it is possible to incorporate a correction for the half-life value into the calibration curve, and so it has become standard practice to quote measured radiocarbon dates and radiocarbon years, meaning that the dates are calculated using Libby's half-life value and have not been calibrated. This approach has the advantage of maintaining consistency with the early papers, and also avoids the risk of a double correction for the Libby half-life value. Carbon exchange reservoir. The different elements of the carbon exchange reservoir vary in how much carbon they store, and in how long it takes for the 14C generated by cosmic rays to fully mix with them. The atmosphere, which is where 14C is generated, contains about 1.9% of the total carbon in the reservoirs, and the 14C it contains mixes in less than 7 years. The ratio of 14C to 12C in the atmosphere is taken as the baseline for the other reservoirs. If another reservoir has a lower ratio of 14C to 12C, it indicates that the carbon is older and hence that some of the 14C has decayed. The ocean surface is an example. It contains 2.4% of the carbon in the exchange reservoir, but there is only about 95% as much 14C as would be expected if the ratio were the same as in the atmosphere. The time it takes for carbon from the atmosphere to mix with the surface ocean is only a few years, but the surface waters also receive water from the deep ocean, which has over 90% of the carbon in the reservoir. Water in the deep ocean takes about 1,000 years to circulate back through surface waters, and so the surface waters contain a combination of older water, with depleted 14C, and water recently at the surface, with 14C in equilibrium with the atmosphere. Creatures living at the ocean surface have the same 14C ratios as the water they live in, and as a result of the reduced 14C/12C ratio, the radiocarbon age of marine life is typically about 400 years. Organisms on land, however, are in closer equilibrium with the atmosphere and have the same 14C/12C ratio as the atmosphere. These organisms contain about 1.3% of the carbon in the reservoir. Sea organisms have a mass of less than 1% of those on land and are not shown on the diagram. Accumulated dead organic matter, of both plants and animals, exceeds the mass of the biosphere by a factor of nearly 3, and since this matter is no longer exchanging carbon with its environment, it has a 14C/12C ratio lower than that of the biosphere. Dating considerations. The variation in the 14C/12C ratio in different parts of the carbon exchange reservoir means that a straightforward calculation of the age of a sample based on the amount of 14C it contains will often give an incorrect result. There are several other possible sources of error that need to be considered. The errors are of 4 general types: variations in the 14C/12C ratio in the atmosphere, both geographically and over time. Isotopic fractionation. Variations in the 14C/12C ratio in different parts of the reservoir. Contamination. Atmospheric variation. In the early years of using the technique, it was understood that it depended on the atmospheric 14C/12C ratio having remained the same over the preceding few thousand years. To verify the accuracy of the method, several artifacts that were datable by other techniques were tested. The results of the testing were in reasonable agreement with the true ages of the objects. However, in 1958, Hessel-Devlers was able to demonstrate that the 14C/12C ratio had changed over time by testing with samples of known ages and showing there was a significant deviation from the expected ratio. This discrepancy, often called the Devlers effect, was resolved by the study of tree rings. Comparison of overlapping series of tree rings allowed the construction of a continuous sequence of tree ring data that spanned 8,000 years. Carbon dating the wood from the tree rings themselves provided the check needed on the atmospheric 14C/12C ratio, with a sample of known date, and a measurement of the value of N. The carbon dating equation allows the calculation of NO the number of atoms of 14C in the sample at the time the tree ring was formed and hence the 14C/12C ratio in the atmosphere at that time. Armed with the results of carbon dating the tree rings, it became possible to construct calibration curves designed to correct the errors caused by the variation over time in the 14C/12C ratio. These curves are described in more detail below. Coal and oil began to be burned in large quantities during the 1800s. Both coal and oil are sufficiently old that they contain little detectable 14C and, as a result, the CO2 released substantially diluted the atmospheric 14C/12C ratio. Dating an object from the early 20th century hence gives an apparent date older than the true date. For the same reason, 14C concentrations in the neighborhood of large cities are lower than the atmospheric average. This fossil fuel effect would only amount to a reduction of 0.2% in 14C activity if the additional carbon from fossil fuels were distributed throughout the carbon exchange reservoir, but because of the long delay in mixing with the deep ocean, the actual effect is a 3% reduction. A much larger effect comes from above-ground nuclear testing, which released large numbers of neutrons and created 14C. From about 1950 until 1963, when atmospheric nuclear testing was banned, it is estimated that several tons of 14C were created. If all this extra 14C had immediately been spread across the entire carbon exchange reservoir, it would have led to an increase in the 14C/12C ratio of only a few percent, but the immediate effect was to almost double the amount of 14C in the atmosphere, with the peak level occurring in about 1965. The level has since dropped, as the bomb carbon percolates into the rest of the reservoir. Isotopic fractionation, photosynthesis is the primary process by which carbon moves from the atmosphere into living things. In both photosynthetic pathways 12C is absorbed slightly more easily than 13C, which in turn is more easily absorbed than 14C. The differential uptake of the three carbon isotopes leads to 13C/12C and 14C/12C ratios in plants that differ from the ratios in the atmosphere. This effect is known as isotopic fractionation. To determine the degree of fractionation that takes place in a given plant, the amounts of both 12C and 13C isotopes are measured, and the resulting 13C/12C ratio is then compared to a standard ratio known as PdB. The 13C/12C ratio is used instead of 14C/12C because the former is much easier to measure, and the latter can be easily derived. The depletion of 13C relative to 12C is proportional to the difference in the atomic masses of the two isotopes, so the depletion for 14C is twice the depletion of 13C. The fractionation of 13C, known as I13C, is calculated as follows, where the A sign indicates parts per thousand. Because the PdB standard contains an unusually high proportion of 13C, most measured I13C values are negative. For marine organisms, the details of the photosynthesis reactions are less well understood, and the I13C values for marine photosynthetic organisms also depend on temperature. At higher temperatures, CO2 has poor solubility in water, which means there is less CO2 available for the photosynthetic reactions. Under these conditions, fractionation is reduced, and at temperatures above 14 degrees Celsius the I13 Celsius values are correspondingly higher, while at lower temperatures, CO2 becomes more soluble and hence more available to the marine organisms. The I13C value for animals depends on their diet. An animal that eats food with high I13C values will have a higher I13C than one that eats food with lower I13C values. The animal's own biochemical processes can also impact the results. For example, both bone minerals and bone collagen typically have a higher concentration of 13C than is found in the animal's diet, though for different biochemical reasons. The enrichment of bone 13C also implies that excreted material is depleted in 13C relative to the diet. Since 13C makes up about 1% of the carbon in a sample, the 13C/12C ratio can be accurately measured by mass spectrometry. Typical values of I13C have been found by experiment for many plants, as well as for different parts of animals such as bone collagen, but when dating a given sample it is better to determine the I13C value for that sample directly than to rely on the published values. The carbon exchange between atmospheric CO2 and carbonate at the ocean surface is also subject to fractionation, with 14C in the atmosphere more likely than 12C to dissolve in the ocean. The result is an overall increase in the 14C/12C ratio in the ocean of 1.5%, relative to the 14C/12C ratio in the atmosphere. This increase in 14C concentration almost exactly cancels out the decrease caused by the upwelling of water from the deep ocean, so that direct measurements of 14C radiation are similar to measurements for the rest of the biosphere. Correcting for isotopic fractionation, as is done for all radiocarbon dates to allow comparison between results from different parts of the biosphere, gives an apparent age of about 400 years for ocean surface water. Reservoir effects. Libby's original exchange reservoir hypothesis assumed that the 14C/12C ratio in the exchange reservoir is constant all over the world, but it has since been discovered that there are several causes of variation in the ratio across the reservoir. Marine effect. The company, 2 in the atmosphere transfers to the ocean by dissolving in the surface water as carbonate and bicarbonate ions. At the same time the carbonate ions in the water are returning to the air as CO2. This exchange process brings 14C from the atmosphere into the surface waters of the ocean, but the 14C thus introduced takes a long time to percolate through the entire volume of the ocean. The deepest parts of the ocean mix very slowly with the surface waters, and the mixing is known to be uneven. The main mechanism that brings deep water to the surface is upwelling. Upwelling is more common in regions closer to the equator. It is also influenced by other factors such as the topography of the local ocean bottom and coastlines, the climate, and wind patterns. Overall, the mixing of deep and surface waters takes far longer than the mixing of atmospheric CO2 with the surface waters, and as a result water from some deep ocean areas has an apparent radiocarbon age of several thousand years. Upwelling mixes this old water with the surface water, giving the surface water an apparent age of about several hundred years. This effect is not uniform. The average effect is about 440 years, but there are local deviations of several hundred years for areas that are geographically close to each other. The effect also applies to marine organisms such as shells, and marine mammals such as whales and seals, which have radiocarbon ages that appear to be hundreds of years old. Hemisphere effect. The northern and southern hemispheres have atmospheric circulation systems that are sufficiently independent of each other that there is a noticeable time lag in mixing between the two. The atmospheric 14C/12C ratio is lower in the southern hemisphere, with an apparent additional age of 30 years for radiocarbon results from the south as compared to the north. This is probably because the greater surface area of ocean in the southern hemisphere means that there is more carbon exchanged between the ocean and the atmosphere than in the north. Since the surface ocean is depleted in 14C because of the marine effect, 14C is removed from the southern atmosphere more quickly than in the north. Other effects. If the carbon in fresh water is partly acquired from aged carbon, such as rocks, then the result will be a reduction in the 14C/12C ratio in the water. For example, rivers that pass over limestone, which is mostly composed of calcium carbonate, will acquire carbonate ions. Similarly, groundwater can contain carbon derived from the rocks through which it has passed. These rocks are usually so old that they no longer contain any measurable 14C, so this carbon lowers the 14C/12C ratio of the water it enters, which can lead to apparent ages of thousands of years for both the affected water and the plants and freshwater organisms that live in it. This is known as the hard water effect, because it is often associated with calcium ions, which are characteristic of hard water. However, there can be other sources of carbon that have the same effect, such as humus. The effect is very variable and there is no general offset that can be applied. The usual way to determine the size of the effect is to measure the apparent age offset of a modern sample. Volcanic eruptions eject large amounts of carbon into the air. The carbon is of geological origin and has no detectable 14C, so the 14C/12C ratio in the vicinity of the volcano is depressed relative to surrounding areas. Dormant volcanoes can also emit aged carbon. Plants that photosynthesize this carbon also have lower 14C/12C ratios, for example, plants on the Greek island of Santorini, near the volcano, have apparent ages of up to 1,000 years. These effects are hard to predict. The town of Accelerator, on Santorini, was destroyed in a volcanic eruption thousands of years ago, but radiocarbon dates for objects recovered from the ruins of the town show surprisingly close agreement with dates derived from other means. If the dates for Accelerator are confirmed, it would indicate that the volcanic effect in this case was minimal. Contamination: any addition of carbon to a sample of a different age will cause the measured date to be inaccurate. Contamination with modern carbon causes a sample to appear to be younger than it really is. The effect is greater for older samples. If a sample that is in fact 17,000 years old is contaminated so that 1% of the sample is actually modern carbon, it will appear to be 600 years younger. For a sample that is 34,000 years old, the same amount of contamination would cause an error of 4,000 years. Contamination with old carbon, with no remaining 14C, causes an error in the other direction, which does not depend on age. A sample that has been contaminated with 1% old carbon will appear to be about 80 years older than it really is, regardless of the date of the sample. Samples for dating need to be converted into a form suitable for measuring the 14C content. This can mean conversion to gaseous, liquid, or solid form, depending on the measurement technique to be used. Before this can be done, however, the sample must be treated to remove any contamination and any unwanted constituents. This includes removing visible contaminants, such as rootlets that may have penetrated the sample since its burial. Alkali and acid washes can be used to remove humic acid and carbonate contamination, but care has to be taken to avoid destroying or damaging the sample. Material considerations: it is common to reduce a wood sample to just the cellulose component before testing, but since this can reduce the volume of the sample to 20% of the original size, testing of the whole wood is often performed as well. Charcoal is often tested but is likely to need treatment to remove contaminants. Unburnt bone can be tested. It is usual to date it using collagen, the protein fraction that remains after washing away the bone's structural material. Hydroxyproline, one of the constituent amino acids in bone, was once thought to be a reliable indicator as it was not known to occur except in bone, but it has since been detected in groundwater. For burnt bone, testability depends on the conditions under which the bone was burnt. If the bone was heated under reducing conditions, it may have been carbonized. In this case the sample is often usable. Shells from both marine and land organisms consist almost entirely of calcium carbonate either as aragonite or as calcite, or some mixture of the two. Calcium carbonate is very susceptible to dissolving and recrystallizing. The recrystallized material will contain carbon from the sample's environment, which may be of geological origin. If testing recrystallized shell is unavoidable, it is sometimes possible to identify the original shell material from a sequence of tests. It is also possible to test contralin, which is an organic protein found in shell, but this only constitutes 1 to 2% of shell material. The three major components of peat are humic acid, humins, and fulvic acid. Of these, humins give the most reliable date as they are insoluble in alkali and less likely to contain contaminants from the sample's environment. A particular difficulty with dried peat is the removal of rootlets, which are likely to be hard to distinguish from the sample material. Soil contains organic material, but because of the likelihood of contamination by humic acid of more recent origin, it is very difficult to get satisfactory radiocarbon dates. It is preferable to sieve the soil for fragments of organic origin, and date the fragments with methods that are tolerant of small sample sizes. Other materials that have been successfully dated include ivory, paper, textiles, individual seeds and grains, straw from within mud bricks, and charred food remains found in pottery. Preparation and size. Particularly for older samples, it may be useful to enrich the amount of 14C in the sample before testing. This can be done with a thermal diffusion column. The process takes about a month and requires a sample about 10 times as large as would be needed otherwise, but it allows more precise measurement of the 14C/12C ratio in old material and extends the maximum age that can be reliably reported. Once contamination has been removed, samples must be converted to a form suitable for the measuring technology to be used. Where gas is required, CO2 is widely used. For samples to be used in liquid scintillation counters, the carbon must be in liquid form. The sample is typically converted to benzene. For accelerator mass spectrometry, solid targets are used. While these are usually graphite, CO2 and iron carbide can also be used. The quantity of sample material needed to perform testing depends on what is being tested and on the testing technology that is being used. There are two types of testing technology: detectors that record radioactivity, known as beta counters, or accelerator mass spectrometers. For beta counters, a sample weighing at least 10 grams is typically required. Accelerator mass spectrometry labs are much more sensitive and can deal with samples as small as 10 milligrams and generally require less than a gram of most sample materials. Measurement and results. For decades after Libby performed the first radiocarbon dating experiments, the only way to measure the 14C in a sample was to detect the radioactive decay of individual carbon atoms. In this approach, what is measured is the activity, in number of decay events per unit mass per time period, of the sample. This method is also known as beta counting, because it is the beta particles emitted by the decaying 14C atoms that are detected. In the late 1970s an alternative approach became available, directly counting the number of 14C and 12C atoms in a given sample, via accelerator mass spectrometry, usually referred to as AMS. AMS counts the 14C/12C ratio directly, instead of the activity of the sample, but measurements of activity and 14C/12C ratio can be converted into each other exactly. For some time, beta counting methods were more accurate than AMS, but there is now little to choose between them. AMS has two significant advantages over beta counting: it can perform accurate testing on samples much too small for beta counting. And it is much faster. An accuracy of 1% can be achieved in minutes with AMS, which is far quicker than would be achievable with the older technology. Beta counting. Libby's first detector was a Geiger counter of his own design. He converted the carbon in his sample to lamp black and coated the inner surface of a cylinder with it. This cylinder was inserted into the counter in such a way that the counting wire was inside the sample cylinder, in order that there should be no material between the sample and the wire. Any interposing material would have interfered with the detection of radioactivity. The beta particles emitted by decaying 14C are so weak that half are stopped by a 0.01 ohm thickness of aluminium. Libby's method was soon superseded by gas proportional counters, which were less affected by bomb carbon. These counters record bursts of ionization caused by the beta particles emitted by the decaying 14C atoms. The bursts are proportional to the energy of the particle, so other sources of ionization, such as background radiation, can be identified and ignored. The counters are surrounded by lead or steel shielding, to eliminate background radiation and to reduce the incidence of cosmic rays. In addition, anti-coincidence detectors are used. These record events outside the counter, and any event recorded simultaneously both inside and outside the counter is regarded as an extraneous event and ignored. The other common technology used for measuring 14C activity is liquid scintillation counting, which was invented in 1950, but which had to wait until the early 1960s, when efficient methods of benzene synthesis were developed, to become competitive with gas counting. After 1970, liquid counters became the more common technology choice for newly constructed dating laboratories. The counters work by detecting flashes of light caused by the beta particles emitted by 14C as they interact with a fluorescing agent added to the benzene. Like gas counters, liquid scintillation counters require shielding and anti-coincidence counters. For both the gas proportional counter and liquid scintillation counter, what is measured is the number of beta particles detected in a given time period. Since the mass of the sample is known, this can be converted to a standard measure of activity in units of either counts per minute per gram of carbon, or becquerels per kg. Each measuring device is also used to measure the activity of a blank sample, a sample prepared from carbon old enough to have no activity. This provides a value for the background radiation, which must be subtracted from the measured activity of the sample which is being dated to get the activity due solely to that sample's 14C. In addition, a sample with a standard activity is measured, in order to provide a baseline for comparison. Accelerator mass spectrometry. AMS counts the atoms of 14C and 12C in a given sample, determining the 14C/12C ratio directly. The sample, often in the form of graphite, is made to emit C ions, which are injected into an accelerator. The ions are accelerated and pass through a stripper, which removes several electrons so that the ions emerge with a positive charge. The C3+ ions are then passed through a magnet that curves their path. The heavier ions are curved less than the lighter ones, so the different isotopes emerge as separate streams of ions. A particle detector then records the number of ions detected in the 14C stream, but since the volume of 12C is too great for individual ion detection, counts are determined by measuring the electric current created in a Faraday cup. Some AMS facilities are also able to evaluate a sample's fractionation, another piece of data necessary for calculating the sample's radiocarbon age. The use of AMS, as opposed to simpler forms of mass spectrometry, is necessary because of the need to distinguish the carbon isotopes from other atoms or molecules that are very close in mass to them, such as 14N and 13CH. As with beta counting, both blank samples and standard samples are used. Two different kinds of blank may be measured: a sample of dead carbon that has undergone no chemical processing, in order to detect any machine background, and a sample known as a process blank made from dead carbon that is processed into target material in exactly the same way as the sample which is being dated. Any 14C signal from the machine background blank is likely to be caused either by beams of ions that have not followed the expected path inside the detector, or by carbon hydrides such as 12CH, 2 or 13CH. A 14C signal from the process blank measures the amount of contamination introduced during the preparation of the sample. These measurements are used in the subsequent calculation of the age of the sample. Calculations. The calculations to be performed on the measurements taken depend on the technology used, since beta counters measure the sample's radioactivity whereas AMS determines the ratio of the three different carbon isotopes in the sample. To determine the age of a sample whose activity has been measured by beta counting, the ratio of its activity to the activity of the standard must be found. To determine this, a blank sample is measured, and a sample of known activity is measured. The additional samples allow errors such as background radiation and systematic errors in the laboratory setup to be detected and corrected for. A common standard sample is HOXII, 1000 lb of which was prepared by NIST in 1977 from French beet harvests. The results from AMS testing are in the form of ratios of 12C, 13C, and 14C. These ratios are used to calculate FM, the fraction modern. This is defined as the ratio between the 14C/12C ratio in the sample and the 14C/12C ratio in modern carbon, which is in turn defined as the 14C/12C ratio that would have been measured in 1950 had there been no fossil fuel effect. Both beta counting and AMS results have to be corrected for fractionation. This is necessary because different materials of the same age, which because of fractionation have naturally different 14C/12C ratios, will appear to be of different ages because the 14C/12C ratio is taken as the indicator of age. To avoid this, All radiocarbon measurements are converted to the measurement that would have been seen had the sample been made of wood, which has a known I13C value of a 25 euro. Once the corrected 14C/12C ratio is known, a radiocarbon age is calculated using. The calculation uses Libby's half-life of 5,568 years, not the more accurate modern value of 5,730 years. Libby Euro unregistered trademark S value for the half-life is used in order to maintain consistency with early radiocarbon testing results. Calibration curves include a correction for this, so the accuracy of final reported calendar ages is assured. Errors and reliability. The reliability of the results can be improved by lengthening the testing time. For example, if counting beta decays for 250 minutes is enough to give an error of a plus or minus 80 years, with 68% confidence, then doubling the counting time to 500 minutes will allow a sample with only half as much 14C to be measured with the same error term of 80 years. Radiocarbon dating is generally limited to dating samples no more than 50,000 years old, as samples older than that have insufficient 14C to be measurable. Older dates have been obtained by using special sample preparation techniques, large samples, and very long measurement times. These techniques can allow dates up to 60,000 and in some cases up to 75,000 years before the present to be measured. Radiocarbon dates are generally presented with a range of 1 standard deviation on either side of the mean. This obscures the fact that the true age of the object being measured may lie outside the range of dates quoted. In 1970, the British Museum Radiocarbon Laboratory ran weekly measurements on the same sample for 6 months. The results varied widely, and included multiple date ranges that did not overlap with each other. The extreme measurements included one with a maximum age of under 4,400 years, and another with a minimum age of over 4,500 years. Errors in procedure can also lead to errors in the results. If 1% of the benzene in a modern reference sample accidentally evaporates, scintillation counting will give a radiocarbon age that is too young by about 80 years. Calibration. The calculations given above produce dates in radiocarbon years, that is, dates which represent the age the sample would be if the 14C/12C ratio had been constant historically. Although Libby had pointed out as early as 1955 the possibility that this assumption was incorrect, it was not until discrepancies began to accumulate between measured ages and known historical dates for artifacts that it became clear that a correction would need to be applied to radiocarbon ages to obtain calendar dates. To produce a curve that can be used to relate calendar years to radiocarbon years, a sequence of securely dated samples is needed which can be tested to determine their radiocarbon age. The study of tree rings led to the first such sequence. Tree rings from individual pieces of wood show characteristic sequences of rings that vary in thickness because of environmental factors such as the amount of rainfall in a given year. These factors affect all trees in an area, so examining tree ring sequences from old wood allows the identification of overlapping sequences. In this way, an uninterrupted sequence of tree rings can be extended far into the past. The first such published sequence, based on bristlecone pine tree rings, was created in the 1960s by Wesley Ferguson. Hans Suess used this data to publish the first calibration curve for radiocarbon dating in 1967. The curve showed 2 types of variation from the straight line, a long-term fluctuation with a period of about 9,000 years, and a shorter-term variation, often referred to as wiggles, with a period of decades. Suess said he drew the line showing the wiggles by cosmic schwung Euro freehand, in other words. It was unclear for some time whether the wiggles were real or not, but they are now well established. A calibration curve is used by taking the radiocarbon date reported by a laboratory, and reading across from that date on the vertical axis of the graph. The point where this horizontal line intersects the curve will give the calendar age of the sample on the horizontal axis. This is the reverse of the way the curve is constructed. A point on the graph is derived from a sample of known age, such as a tree ring. When it is tested, the resulting radiocarbon age gives a data point for the graph. Over the next 30 years many calibration curves were published using a variety of methods and statistical approaches. These were superseded by the integral series of curves, beginning with INTCAL 98, published in 1998, and updated in 2004, 2009, and, most recently, 2013. The improvements to these curves are based on new data gathered from tree rings, VUVs, coral, and other studies. The INTCAL 13 data includes separate curves for the northern and southern hemispheres, as they differ systematically because of the hemisphere effect. There is also a separate marine calibration curve. For a set of samples with a known sequence and separation in time such as a sequence of tree rings, the sample's radiocarbon ages form a small subset of the calibration curve. The resulting curve can then be matched to the actual calibration curve by identifying where, in the range suggested by the radiocarbon dates, the wiggles in the calibration curve best match the wiggles in the curve of sample dates. This wiggle matching technique can lead to more precise dating than is possible with individual radiocarbon dates. Wiggle matching can be used in places where there is a plateau on the calibration curve, and hence can provide a much more accurate date than the interceptor probability methods are able to produce. The technique is not restricted to tree rings. For example, a stratified tephra sequence in New Zealand, known to predate human colonization of the islands, has been dated to 1314 AD or plus or minus 12 years by wiggle matching. Bayesian statistical techniques can be applied when there are several radiocarbon dates to be calibrated. For example, if a series of radiocarbon dates is taken from different levels in a given stratigraphic sequence, Bayesian analysis can help determine if some of the dates should be discarded as anomalies, and can use the information to improve the output probability distributions. Reporting dates. Several formats for citing radiocarbon results have been used since the first samples were dated. As of 2014, the standard format required by the journal Radiocarbon is as follows. Uncalibrated dates should be reported as laboratory 14C era plus or minus range BP, where laboratory identifies the laboratory that tested the sample, and the sample ID. Less than 14C year is the laboratory's determination of the age of the sample. In radiocarbon years, range is the laboratory's estimate of the error in the age, at 1 i-florin confidence. BP stands for before present, referring to the reference date of 1950, so that 500 BP means the year 1450 AD. For example, the uncalibrated date UTC 2020, 3510 plus or minus 60 BP indicates that the sample was tested by the Utrecht van der Graaf Laboratorium, where it has a sample number of 2020, and that the uncalibrated age is 3510 years before present, a plus or minus 60 years. Related forms are sometimes used, for example, 10 car BP means 10,000 radiocarbon years before present, and 14 Ca BP might be used to distinguish the uncalibrated date from a date derived from another dating method such as thermoluminescence. Radiocarbon gives two options for reporting calibrated dates. A common format is cal date range confidence, where date range is the range of dates corresponding to the given confidence level. Confidence indicates the confidence level for the given date range. For example, cal 1220 euro 1281 AD means a calibrated date for which the true date lies between 1220 AD and 1281 AD, with a confidence level given as 1 i-florin, or 1 standard deviation. Calibrated dates can also be expressed as BP instead of using BC and AD. The curve used to calibrate the results should be the latest available integral curve. Calibrated dates should also identify any programs, such as OxCal, used to perform the calibration. In addition, an article in Radiocarbon in 2014 about radiocarbon date reporting conventions recommends that information should be provided about sample treatment, including the sample material, pre-treatment methods, and quality control measurements. That the citation to the software used for calibration should specify the version number and any options or models used. And that the calibrated date should be given with the associated probabilities for each range. Use in archaeology, interpretation. A key concept in interpreting radiocarbon dates is archaeological association. What is the true relationship between two or more objects at an archaeological site? It frequently happens that a sample for radiocarbon dating can be taken directly from the object of interest, but there are also many cases where this is not possible. Metal grave goods, for example, cannot be radiocarbon dated, but they may be found in a grave with a coffin, charcoal, or other material which can be assumed to have been deposited at the same time. In these cases, a date for the coffin or charcoal is indicative of the date of deposition of the grave goods, because of the direct functional relationship between the two. There are also cases where there is no functional relationship, but the association is reasonably strong. For example, a layer of charcoal in a rubbish pit provides a date which is a relationship to the rubbish pit. Contamination is of particular concern when dating very old material obtained from archaeological excavations, and great care is needed in the specimen selection and preparation. Jaime al have suggested that many of the dates published for Neanderthal artifacts are too recent because of the contamination by young carbon. As a tree grows, only the outermost tree ring exchanges carbon with its environment, so the age measured for a wood sample depends on where the sample is taken from. This means that radiocarbon dates on wood samples can be older than the date at which the tree was felled. In addition, if a piece of wood is used for multiple purposes, there may be a significant delay between the felling of the tree and the final use in the context in which it is found. This is often referred to as the old wood problem. One example is the Bronze Age trackway at Withy Copse, in England. The trackway was built from wood which had clearly been worked for other purposes before being reused in the trackway. Another example is driftwood, which may be used as construction material. It is not always possible to recognize reuse. Other materials can present the same problem. For example, bitumen is known to have been used by some Neolithic communities to waterproof baskets. The bitumen's radiocarbon age will be greater than is measurable by the laboratory, regardless of the actual age of the context. A separate issue, related to reuse, is that of lengthy use, or delayed deposition. For example, a wooden object that remains in use for a lengthy period will have an apparent age greater than the actual age of the context in which it is deposited. Impact. Soon after the publication of Libby's 1949 paper in Science, radiocarbon dating laboratories were being established at universities around the world, and by the end of the 1950s there were over 20 active 14C research laboratories. It was quickly apparent that the principles of radiocarbon dating were correct, despite discrepancies whose cause was not then known. The development of radiocarbon dating has had a profound impact on archaeology. It is often described as the radiocarbon revolution. In the words of anthropologist R.E. Taylor, 14C data made a world prehistory possible by contributing a timescale that transcends local, regional and continental boundaries. It provides more accurate dating with insights than the previous methods, which were usually derived from either stratigraphy or typologies. It also allows comparison and synchronization of events across great distances. The advent of radiocarbon dating may even have led to better field methods in archaeology, since better data recording leads to firmer association of objects with the samples to be tested. These improved field methods were sometimes motivated by attempts to prove that a 14C date was incorrect. Taylor also suggests that the availability of definite date information freed archaeologists from the need to focus so much of their energy on determining the dates of their finds, and led to an expansion of the questions archaeologists were willing to research. For example, questions about the evolution of human behavior were much more frequently seen in archaeology, beginning in the 1970s. The dating framework provided by radiocarbon led to a change in the prevailing view of how innovations spread through prehistoric Europe. It had previously been thought that many ideas spread by diffusion through the continent, or by invasions of peoples bringing new cultural ideas with them. As radiocarbon dates began to prove these ideas wrong in many instances, it became apparent that these innovations must sometimes have arisen locally. This has been described as a second radiocarbon revolution, and with regard to British prehistory, one archaeologist has characterized the impact of radiocarbon dating as radical therapy for the progressive disease of invasionism. More broadly, The success of radiocarbon dating stimulated interest in analytical and statistical approaches to archaeological data. Occasionally, radiocarbon dating techniques are used to date an object of popular interest. An example is the Shroud of Turin, a piece of linen cloth thought by some to bear an image of Jesus Christ after his crucifixion. The Shroud of Turin was tested in 1988. The results, from 3 separate laboratories, dated the sample of linen tested to the 1300s, raising doubts about the authenticity of the shroud. Other radioactive isotopes created by cosmic rays have been studied to determine if they could be used to assist in dating objects of archaeological interest. These include 3He, 10B, 21Ni, 26Al, and 36 centiliters. With the development of AMS in the 1980s, it became possible to measure these isotopes precisely enough for them to be the basis of useful dating techniques. They have been primarily applied to dating rocks. Naturally occurring radioactive isotopes can also form the basis of dating methods. This is the case with potassium-argon dating, argon-argon dating, and uranium-Ceres dating. Other dating techniques of interest to archaeologists include thermoluminescence, optically stimulated luminescence, electron spin resonance dating, and fission track dating, as well as techniques that depend on annual bands or layers, such as dendrochronology, tephrochronology, and varvchronology. Notes. Footnotes. References: Aitken, M.J. Science-Based Dating in Archaeology. London, Longman. ISBN A0-582-49309-9, Bianchi, Thomas S. Canuel, Elizabeth. A Chemical Markers and Aquatic Ecosystems. Princeton, Princeton University Press. ISBN A978-0-691-13414-7. Bowman, Sheridan, 1990. Radiocarbon Dating. London, British Museum Press. ISBN A0-7141-2047-2. Burke, Heather. Smith, Claire. Zimmerman, Larry J. The Archaeologist's Field Handbook. Lanham, Maryland, Altamira Press. ISBN A978-0-7591-0882-0. Cronin, Thomas M. Paleoclimates, Understanding Climate Change Past and Present. New York, Columbia University Press. ISBN A978-0-231-14494-0. Das, Chable. Fundamentals of Contemporary Mass Spectrometry. Hoboken, N.J., John Wiley & Sons. ISBN A978-0-471-68229-5. Eriksson Stenstra. Paragraph M, Christina. Skog, Gar. Paragraph Ran. Georgiado, Elisavit. Genberg, Johan. Johansson, Annette. A Guide to Radiocarbon Units and Calculations. Lund, Lund University. Ferentsky, V.I. Polyakov, V.A. Isotopes of the Earth's Hydrosphere. New York, Springer. ISBN A978-94-007-2855-4. Angstrom Ilar, Jan. Application of Environmental Radionuclides in Radiochronology, Radiocarbon. Interkfor, Richard. Berg, Dieter. Man-Made and Natural Radioactivity in Environmental Pollution and Radiochronology. Dordrecht, Kluwer. Academic Publishers PPA 150 €179. ISBN A1-4020-1860-6. L'Annonciator, Michael F. Radioactivity, Introduction and History. Amsterdam, Elsevier. ISBN A978-444-52715-8. L'Annonciator, Michael F. Kessler, Michael J. Liquid Scintillation Analysis, Principles and Practice. In L'Annonciator, Michael F. Handbook of Radioactivity Analysis. Oxford, Academic Press PPA 423 €573. ISBN A978-01-2-384873-4, Libby, Willard F. 1952. Radiocarbon Dating ed. Chicago, Phoenix A. Mullaney, Mary E. A Consumer's Guide to Archaeological Science. New York, Springer. ISBN A978-1-4419-5704-7 Marslin, Mark A. Swan, George H. Isotopes in Marine Sediments. Inleng, Melanie J. Isotopes in Paleoenvironmental Research. Dordgt, Springer PPA 227 Euro 290. ISBN A978-1-4020-2503-7 Mook, W.G. Waterboak, H.T. Handbooks for Archaeologists, No. 3, Radiocarbon Dating. Strasbourg, European Science Foundation. ISBN A2-903148-44-9 Post, Wilfred M. Carbon Cycle. In Gowdy, Andrew. Cuff, David J. Encyclopedia of Global Change, Environmental Change and Human Society, Volume 1. Oxford, Oxford University Press PPA 127 Euro 130. ISBN A0-19-514518-6 Raskazov, Sergei 5. Brandt, Sergei Borisovich. Brandt, Ivan S. Radiogenic Isotopes and Geologic Processes. Dordgt, Springer. ISBN A978-90-481-2998-0 Scherninger, Margaret J. Diet Reconstruction and Ecology Using Stable Isotope Ratios. In Larson, Clark Spencer. A Companion to Biological Anthropology. Oxford, Blackwell PPA 445 Euro 464. ISBN A978-1-4051-8900-2 Suez, H. E. Bristlecon Pine Calibration of the Radiocarbon Timescale 5200 BC to the Present. In Olson, Ingrid U. Radiocarbon Variations and Absolute Chronology. New York, John Wiley & Sons PPA 303 Euro 311 Taylor, R.E. Radiocarbon Dating. London, Academic Press. ISBN A0-12-433,663-9 Taylor, R.E. Radiocarbon Dating. In Taylor, R.E. Aitken, Martin J. Chronometric Dating in Archaeology. New York, Plenum Press PPA 65 Euro 97. ISBN A0-306-45715-6 Terrace Me, J. Radiocarbon Dating, Some Problems and Potential Developments. In Mahaney, W. C. Quaternary Dating Methods. Amsterdam, Elsevier PPA 1 Euro 15. ISBN A0-444-42392-3 Theodor Kubler SSON, PAR LL. Measurement of Weak Radioactivity. Singapore, World Scientific Publishing. ISBN A97810223153 Trumbore, Susan E. Applications of Accelerator Mass Spectrometry to Soil Science. In Bhutan, Thomas W. Yamasaki, Shinichi. Mass Spectrometry of Soils. New York, Marcel Decker PPA 311 Euro 340. ISBN A0-8247-9699-3 Tunis, C. Zoppi, U. Barbetti, M. Radionuclide Dating in Archaeology by Accelerator Mass Spectrometry. In Martini, M. Milazzo, M. Santini, M. Physics Methods in Archaeometry. Amsterdam, iOS Press PPA 385 Euro 405. ISBN A978-1-58603-424-5 Walker, Mike. Quaternary Dating Methods. Chichester, John Wiley & Sons. ISBN A978-0-470-86927-7 Warnock, Peter. Chemistry of the Natural Atmosphere. London, Academic Press. ISBN A0-12-735632-0. External links, Radon, Database for European 14C dates.